let's get started. So let's see here. In terms of announcements, I think your next nano quiz, beginning of next week. You see a pattern here, but check the schedule as usual. Your next homework is due Wednesday of next week. Is that right? Yeah. And you should have all the material you need for that. To those of you who are watching through the camera right now, this classroom is pretty empty. I give you these videos as a courtesy for students who have to miss class, but there's nothing worse than lecturing to an empty room. So, I don't know. You're strongly encouraged to attend, and if you stop posting those, it's your responsibility. Are there any questions about procedural stuff? I think basically your two responsibilities for now are turning your homework and preparing for your nano quiz. Okay, excellent. Right, well, in that case, let's get started today and talk about some of my favorite topics in the computer graphics world, which is physics. And so today we'll talk about particle systems, which is a pretty typical thing to do in the video game world. And then in our next lecture, we'll talk specifically about simulating some physical phenomena that we do in your SSM. We'll talk about cloth and hair and how those get solved in practice. Okay. So if you remember from our last lecture, we talked about a lot of different types of animation, right? And mainly the machinery that we developed basically for the first couple weeks of this course gave us everything that we needed to do keyframing style animation. Right? Remember that keyframing, the idea is we specify sort of important poses that are well separated in time, and then we use machinery like splines to fill in between. Yeah? So it's a little bit of a review. Of course, some other types of animations we talked about include procedural animation, where you write a piece of code to generate a 3D model and maybe simulate its motion over time. And then another thing that we'll talk about today is physically based animation. Right? And so physically based animation is how we see smoke and water and fire and sparks and all these cool things in movies. And notice that this is a very politically phrased term here. These are physically based or physically inspired animation tools. They're not by any means attempting to capture something that you could replicate in an experiment. Right? The goal is to fool your eye into thinking you could. Right? And these are different goals. But at the same time, a lot of the tools that we'll cover here really are used in physical simulation practice. These are not that far apart. But there is a bit of more of a trade-off here in terms of the quality, because speed matters for us. Is there questions? Excellent. So there are lots of other types of physically based animation other than the ones that we'll cover today in the next class. If you like these kinds of things, of course there are all kinds of cool fluid mechanical models, finite elements, which deals with rigid objects and bendy things and so on. If you like that kind of stuff, you should look at the mechanical engineering department. Has a lot of courses on that sort of simulation, as well as the EE side of our department. My own class covers a little bit of the finite element method, but that's not really our focus here. This is also, these things tend to be kind of popular in course projects in this class. If you do fluid simulation for your course project, be warned that like 2/3 of your colleagues will too. So if you're aiming for that SIGGRAPH award, to go get your trip to LA this year? Yeah, last year was Vancouver. Then you're going to have to do something pretty fancy. Yeah? Okay, so today we'll be talking about physically based animation, and the basics of physically based animation are more or less what you'd expect, right? We simulate physics by solving the equations of motion, right? And these are exactly what you guys saw in whatever the heck physics class is that MIT undergrads are supposed to take. I haven't any idea what the numbers are. But in any event, all these equations that essentially come from F equals ma are going to come back into play here. And that's true even not just for rigid bodies, but also for fluids, plastic deformation, and so on. Of course, the trade-off here is that physically based animation is physically based on the one hand, right? So if our goal is to have a realistic movie effect, and what we care about is our Pacific Rim dudes fighting the water, and the water splashing everywhere, and fire and smoke and so on, then we really are trying to capture some physical motion. But on the other hand, it's extremely difficult to control. Right? And this is a challenge that's kind of unique to the graphics world, right? So for instance, there are a lot of pieces of research and software tools out there that do really bizarre things like, I have a bag full of I don't know, toys in my kid's room, and I drop them on the floor, and when I drop them on the floor, they spell out a word. Right? I think this is kind of a trope in the animation world. Obviously, physically, that makes no sense, right? The probability of coming up with just the right initial conditions so that final condition should happen is extremely unstable, difficult to solve a problem. So maybe rather than solving that problem so that you could replicate it with an actual bag of toys, instead, maybe you just tweak physics a little bit so that this happens, but the eye doesn't notice that it's a little edit. Okay? And that's where this difficult to control aspect comes in. Right? On the one hand, you'd like to look physical. On the other hand, you'd like to be able to control the narrative in your story. And those two things are often at odds with one another. Right. So in terms of different types of physical dynamics, there are many, and probably these are terms you already saw in physics class. Right. So the one that you spend the most time studying when you take the intro physics class, or probably even in high school, is point dynamics. Right. These are just little idealized pieces of mass sitting in some location in space. Maybe they don't even have an orientation. They're just, like when you talk about gravity and planets orbiting one another, I think this is the typical model. And then if you want to step it up a tiny bit, you talk about rigid bodies. Right? So now this isn't just all of your mass concentrated at some unoriented point, but rather a rigidly moving object that has things like moments of inertia. And then, of course, the thing that we really care about in the computer graphics world is melting 3D bunnies. And to do that, you need to have deformable things, maybe changes in topology, like I have a donut, and it melts, and eventually the hole in the donut kind of closes up. All of these things happen in physics, and handling each one of them is extremely challenging in the graphics pipeline. So today we're going to sit mostly at the top, and then we're going to mention the other two in the next lecture or two before moving on to rendering. Okay, so so our focus today is on point dynamics, and certainly in computer graphics, at least as was 20, 30 years ago, this was basically all you saw, especially in the real-time rendering tools, and these particle systems really came from things like simulating the moon orbiting around the Earth and so on. And of course, in video games, probably that isn't exactly the physics we're trying to capture. But even with some very simple rules and a little bit of sleight of hand, we can get fairly plausible dynamics with very little CPU work, which is really what we're after here. Okay? And so, for example, here's kind of a nice-ish looking water fountain, you might say, a little bit psychedelic coloring. And here, the particles, there isn't even any physical law of motion here at all. They're just like moving on parabolas and placed in a careful way, right? And that's the sort of tricks that people often do in this area. So in the particle systems world, there's some vocabulary words that are worth knowing. So typically, a particle system is consisted of a few different pieces here, right? So on the one hand, you have an object called an emitter, right? So like in the animation I just showed you, that would be like maybe the location that's spewing out those particles that are going to become your water fountain. You have some external forces, like a force field. This is something that we don't experience in real life too often, right? Like as much as I like you guys, I can't feel your gravitational pull from where I'm standing too well. But oftentimes this is some way to kind of control the dynamics in our system. There's just forces sitting in 3D that are kind of guiding our particles around. As well as perhaps designing our force field so that different particles interact, right? That'll be largely the topic of our next lecture. And then the other keyword that we use a lot, and I think is slightly different from what you're used to hearing in calculus class, is that we'll be integrating the laws of mechanics. And here, integrate really does sound like integral, and indeed there's a close connection to this thing that you learn in calculus class. But the basic idea is that when you solve the equations of motion, F equals ma is a differential relationship, right? It's telling you how to determine the acceleration of an object based on stuff going on nearby. But at the end of the day, we don't want the acceleration, right? We want position, and so there's an integral that has to happen to cancel those things out. Yeah. And then, of course, something that happens in particle systems quite a bit is a bit of stochasticity or randomness. Which is to say that there's a lot of random stuff in the real world that we can't control for, so oftentimes we hack it by just perturbing our points of difference. Yeah? And this is used to create all kinds of effects, everything from fluids to, it's not very easy to see on the screen here, but things that look kind of like fire and so on. So for instance, here is that sort of perturbation of the previous thing that we saw. And so if we go back to our vocabulary from before, right, the emitter is the head of the sprinkler here. These particles are like these little points of water mass that are flying around. one more thing that we need to think about from a computational complexity standpoint is, I gave you an emitter, but I didn't give you anything that absorbs particles, right? So if I ran my video game too long, I could overflow memory on my computer. So typically there's some queue that sits behind the scenes that says just, kill a particle that's been around too long. In this case, maybe once the particle goes below the ground level, we know that it's kind of absorbed in the grass or something. But I think you guys could communicate here. So here's a virtual sprinkler. In this case, I think there are no forces other than gravity. So in effect, all these particles are just moving independently, but just by adding some randomness, it's a pretty convincing effect. Yeah. You'll be hearing a lot of sentences like that. Here's a particle system for fire. If I recall, this particular simulation is actually not at all based on the dynamical system for fire. It was just purely phenomenological. Somebody said, like, well, fire particles probably kind of want to go up, and if they interact too much, they swirl around. So they come up with some reasonable rules for how that might happen. And then I believe what's going on is they just look at the y-coordinate and they say, well, if you're low, you're yellow. If you're medium, you're red. If you're high, you're gray. And out comes a pretty convincing fire effect. Could you light a fire in your backyard and capture a video sequence that looks just like this? Probably not. But anyway, enough already. Can any of you guys think of applications of particle systems that are not just, earth, wind, fire, and water? Or like whatever the other missing Power Rangers are. Yeah?
I don't know if that's Power Ranger, but like leaves from trees.
Leaves from trees, absolutely. Yeah. Mm-hmm.
Swirling galaxies.
Swirling galaxies.
Sparks.
Sparks, yeah.
I was going to say.
You just cool. How about things that are physical? So flocks of birds is a great example, right? Roughly these birds are moving around, they have position and orientation, and it kind of depends on just the stuff that's nearby. Crowds of people, is a big one. In fact, if you want like a good tip of a really interesting iceberg on Wikipedia, there's this interesting effect that happens in crowds of people that like when you exceed a certain number of people per square foot, humans start to act a lot like fluids. Like there's a fluid dynamical thing that'll happen. Like if I bump into my neighbor, they'll bump into their neighbor, and so on. And this is actually a very well studied phenomenon, especially for designing things like stadiums, where if there's an emergency and you have to exit really quickly, then all of a sudden everybody collapses in on the door. And it turns out the relevant thing to study is not necessarily like human psychology or directing people to the right place, but actually fluid dynamics, because that's really how people are behaving. And there's some great examples of that gone wrong, right? Like where somebody's designed a stadium the wrong way and nobody can exit and people get trapped and so on. But anyway, to keep things a little cheerier, indeed, one of the key applications of particle systems that I think is a little bit non-obvious is actually in simulating crowds of people or virtual characters. And there's a lot of sort of dynamical rules that happen there, right? I mean, obviously, I don't want to step too close to any of my colleagues in the row, so there's some repelling force there. It's nothing personal. At the same time, maybe there's some force that's directing me to the fact that like I really like to talk to Larry, and he's a cool guy, and so on, right? In fact, this is a thing that people study quite a bit. So there was a SIGGRAPH paper, I believe, 2 years ago, which was totally outside of my discipline. My background is in differential geometry, but I really enjoyed watching where like you have two people walking down a hallway, and the width of their shoulder is, the sum of the width of their shoulder is bigger than the width of the hallway, right? So something has to happen, right? You have to kind of rotate 90 degrees, walk past each other, and keep going. And there are all of these these guys were kind of carefully working out what are the right social norms. How far do you turn? Do men and women turn differently? Or is there something having to do with your body structure, or your job title, or whatever? And these things actually matter for capturing these phenomena, right, in the virtual environment. Okay. In our next class, we'll talk about a different type of particle system where the particle is really composed of some larger object, for example, a piece of cloth. Right, so a very typical way to simulate a piece of cloth is that it's a triangle mesh, and I kind of think of every edge of that mesh as a little spring that wants the triangle not to spread out or shrink too much. Again, as our sanity check, does a big network of springs have anything to do with how an actual piece of cloth behaves? False, it does. So to first order, these are actually the same. But there are a lot of other phenomena that aren't captured here, right? So for instance, cloth tends to have stiffness, right? I can fold it, more than 90 degrees, and it starts to resist that motion, right? And if I have two springs that share, are on two triangles, and they hinge on an edge, like really bizarre things can happen, right? Like here, they're perfectly happy to hinge. The springs don't get messed up at all, but in this direction, they do. Right? So if you're not careful with your cloth simulation, you can get some really strange anisotropic behavior you wouldn't expect. Yeah? And in fact, if you watch old movies until I'd say maybe 15 years ago, in the animated world, the cloth always looks super stiff and like a little bit like cardboard, and that's typically what's going on there. That said, a lot of modern systems for this do a remarkable job. So here, these folks have simulated this piece of cloth. They've dealt with the collision between the cloth, the floor, the ball, and more importantly, what collision have I forgotten? The cloth in itself, which actually is the key determining factor in the shape of this thing, as well as frictional forces and so on. Okay. Order of magnitude, how many seconds per frame do you think it takes to make a simulation like this? 100. Yeah, more than that. These are really, really complicated calculations. Okay? You're unlikely to see cloth like this in a video. Okay. Particles are also used to simulate fluids. In fact, this is a technique that's used not just in computer graphics as a hacky way to like simulate a thing of water, but it actually really is a perfectly legitimate approach to numerical partial differential equation. The basic idea here is that you think of water as sort of a big pile of a bunch of little blobs of fluid, and then you're going to simulate how those blobs are interacting with one another. This technique is called smoothed particle hydrodynamics, SBH. And it's another popular project in this course because it kind of looks like an extension of one of your assignments, but it's actually extremely hard to get SBH fluids to look good. That aside, actually one of the interesting challenges in smooth particle hydrodynamics is like, do I want to render this as a big pile of spheres? No, right? I still want to render it as some fluid, right? So there's actually a geometric component to this problem, which is I draw a bunch of little balls, I take their union, and now I have some interesting shape, which is my fluid surface. And that's the thing that I want to render with refraction and all that cool stuff. Yeah. A key vocabulary word, and one that shows up a lot in the particle system world, is that particle systems are Lagrangian. Right? Hopefully you guys have heard of Lagrange, he's a famous mathematician. Yeah? Basically, there are two physical views of the world, and this goes back to far before computers, right? There's the Lagrangian view of the world and the Eulerian view of the world. Yeah? So the typical example here is to think about a big tank of water, sloshing around. So the Lagrangian view of the world would say, my big tank of water is a big tank of particles, and the thing that I'm going to simulate is sort of for every particle at time 0, where that particle is at time t. Right? So that's the Lagrangian view of the world, and so you have little packets of fluid. Anybody have any idea what the Eulerian view of the world is? These actually play out mathematically. It's not just a coding problem. This would be like I'm a barnacle standing put inside of the bucket of fluid somewhere, and I'm just counting the number of things that move past. Right? And these are two completely equivalent views of the world. Right? One of them moves with the particle, and the other stays in one spot and counts the number of particles that move past. Yeah? And you're probably seeing these mathematically. So, for instance, SBH and particle techniques are pretty clearly Lagrangian, right? You're really simulating stuff moving around. A different way that people often simulate smoke is they'll just have a grid sitting in 3D that doesn't move, right? And every point on the grid has a density of the smoke and a velocity, and that's what gets updated over time. And so that would be an example of Eulerian technique. Incidentally, Eulerian techniques tend to be much easier to code. Right. But in any event, SBH fluids aren't just like cute toys. They really are implemented in most animation software. If you download Maya, you can. And the really exciting things that you can do here, for instance, are try to couple these effects. Right? So maybe you have an Eulerian fluid to simulate the big waves in your water because that kind of happens over some fixed grid. But then when the water hits into the lighthouse here, it sends off all this spray, and maybe the spray makes more sense to deal with in particle systems. And there's this sort of interesting combinatorial explosion that happens in this literature. Like, I take this physical object and smash it into that one, and now I want to simulate it, right? So you can imagine taking an Eulerian fluid and having it release a spray into the air, and then typically maybe the spray just gets thrown away. And then in your next research paper, you take the spray and you say, well, actually, that has some small effect on the Eulerian fluid. So I'm going to try to capture that next. And then after that, I'm going to light the surface of my fluid on fire and drop a rigid object in it, or whatever. It's an easy way to create lots of research. On the real-time graphics side, particles are more important because they're simple, right? And so, for instance, if you want to simulate drooling boxers, there's no better way than using a technique like that. And it's actually pretty convincing. So let's play a little clip of what this looks like. This contains some content that is inappropriate for children. I apologize. So, oh, and I bumped into the tune. Even turn up the dramatic tunes for what matters. It's really fun. Like this whole advertisement is just for like the drool that happens in this video game. So I think it's worth watching. Right? That like this is what was getting people in graphics really excited. Right? There's a new physics engine for punching people. Right. And so you guys can see the particles that are coming off as they're hitting to each other. It's actually an interesting example of physical simulation all the way around. Like, notice that his possible has to kind of slide off of the character, which, from like a sort of interaction standpoint, is pretty tricky. It's faster than ever, but my laptop can't handle it. Yeah. Right. So, in any event, yeah, these are all things that people work very hard on, even though they probably just zip past when you're, playing them in your video game. Right, so hopefully I've convinced you guys that particles aren't just some nice toy. They really do capture a lot of physical effects. Another good one is hair. This is some human body where they've glued on a very voluptuous hairstyle, and they have these tests where they shake the head back and forth. Incidentally, does anybody know the data set? Do you recognize this here? This is a very famous data set in computer graphics. It's actually, I believe the Texas Chainsaw Murderer. Is that who this is? You know, they dedicated his body to science and sliced it up so they have a very detailed scan, a scan of his body, and they use it for a lot of simulation tests. I'm here to tell you guys all the important information. Okay, so at the end of the day, particles is some big collection of point-like masses. We have these generators or emitters, and some external force field that oftentimes your particles are independent, but not always, and often they have lifetimes because at the end of the day, you don't want to overload your CPU. Yep. And I think something that you've now seen a little bit is that just because you're simulating the particles as little points moving around doesn't mean you have to render them that way. Right? So for instance, in SBH, we're simulating a fluid as a big collection of little dots moving around, but at the end of the day, we can glue them all together and we make one fluid surface like that. Incidentally, does anybody have any guess of the hardest test case for smooth particle hydrodynamics? Like, if you really want to break one of these systems? It's actually still water, right? Because if you think about it, the surface of this thing is a bunch of little spheres, and it really wants to flatten itself out, but it can't because it's composed of a bunch of little spheres, okay? And so by the time you start to see all this little wiggling that happens right on the surface, it's another good way to spot a bad graphic system. Okay, so let's talk about our sprinkler a little bit. Yeah, so maybe we have a big linked list of particles, right? We use a linked list as our data structure because we are going to keep adding more and more particles to our list. We don't know how many we need at any given time. And maybe we have some kind of randomness parameters that tell us, the different range of initial velocities we can have, the different colors, whatever. And now for every time step, we're going to follow a couple of things, right? Maybe we generate a bunch of particles sitting at the source, right? So for each particle, we'll make it a new guy. We'll sit them right at the origin, which is apparently where our sprinkler is sitting. And maybe, what does this say? This is saying that I have a velocity that points up, right? In this case, I think they're taking the convention that the z-coordinate is this way. And then this spread parameter is just saying I'm going to randomly generate some perturbation of the up vector, scale it by, in this case, 0.1. And that's going to be the initial velocity of my particle. Right? Because it would be a really boring sprinkler if everything went straight up. And similarly for the color. And then I'm going to add it to my linked list. Okay, so at every time step, I'm just going to generate k new particles. And then what do I have to do next? Well, next I have to like actually move these things. Yeah? And so that's what we do next. So we're going to link, we're going to loop over our linked list here. And we can change the position by adding the change in time as a velocity. Hopefully we can all agree that's a reasonable thing to do. And then in this case, maybe we subtract gravity times the change in time from velocity. Right? This is Newton's law, right? That d velocity dt is minus gravity. And then we just drop it. Does this particle system make sense? This is just kind of pseudocode, but it's within a simplest thing. Okay. Right, and in fact, I included a link in the slides to a little processing applet you can use and play with this thing. This one's not interactive. We'll have one later that it's we'll differ. Okay, so this is our first example of a system that solves something called an ordinary differential equations. How many of us have seen ODEs before and some about that? Probably most of you guys. Even if you haven't or if you've forgotten, that's okay. We'll remind you how this stuff works. Okay. And in particular, it's going to take this kind of canonical form up here. So we have an unknown vector x as a function of time. And we're going to say dx dt equals some function of x in time. What's wrong here? What does Newton's law look like? Newton's third law? Second? Third? It's third. Yeah, Newton's third law is F equals ma. Where's the a here? There ain't none. Right? So there seems to be a little bit of a contradiction. So we're going to have to go back and fix that. Right? But in any event, what we're going to focus on today is solving something called an initial value problem, where the idea is I'm given the configuration of my system at time t0, and my job is to predict it for bigger t. Okay. Anybody know what the opposite of an initial value problem is? Boundary value problem. Right? So this would be like, I have the configuration of my system at 2 points in time, and I'd like to fill in what happens in between. Boundary value problems pop up a ton in computer graphics, right? Because we want to control things at lots of times. Okay, so in Newtonian mechanics, as hopefully most of you guys know, we have F equals ma, or if I take all of my particle positions, put on big vector x, then we know that the second derivative in t is proportional to force. Hopefully none of this comes as a surprise. And so one way to think about it is that both position and force are vectors that change in time, but typically we know the force as a function of the configuration of positions, velocities. Yep. Okay, and remember, so in today's lecture we're going to be a little bit sloppy and not keep writing like x of t, but by default all variables here except time, well even time, is a function of time. Okay? Right. So, how are we going to take Newton's laws and make it look like this form here? So here's one way to do it. So let's make a new variable, call him b, and he'll be x prime. Yeah? Okay, and we know that F equals ma, and we'll say force is maybe a function of position and velocity equals m times acceleration, so second derivative. So here's this thing. Can anybody come up with a different expression for x double prime using my definition here? It's b prime, right? B prime is x double prime. Cool. So in other words, this is m b. Cool. So we're going to do a little mathematical sleight of hand here. And we're going to say that, in fact, Newton's law is first order if we just make a change of variables. We're going to say d over d time of x and b. We're going to say that rather than having just our variable be x, we're going to make two variables, x and b. So in other words, I'm going to double the size of my problem. But that's okay, it's still an ODE. And what is x prime? It's b. And what's b prime? It's f of x. See what I did there? This is the same as what we started with. So here's the thing. This problem, the way I've written it, is a first order ordinary differential equation. Right? There's only one derivative. Do you guys see this trade-off that we can do? We can either have more derivatives or more variables, so these are kind of the same thing. And so the basic hack here is anytime I would like a higher derivative, I'm going to say I'm going to make a new variable, which is like the first derivative of x. And well, there's a first order relationship between these two guys. And now there's a zeroth order relationship in terms of x. Cool? This is a sneaky trick. This is just a change in notation. So here's the thing. If I have a piece of software that can reliably solve only first order ordinary differential equations, in a sense I'm kind of happy, right? Because I know I can apply this trick, and if I have some higher order problem, like Newton's law, I can use my piece of software just with like a larger dimensional problem and solve that too. Does that make sense? So today we're going to talk a lot about algorithms for solving first order ODE, and something to keep in the back of your head is that even though we're talking about first order stuff, it still applies to f equals f. Yeah, that's the basic takeaway here. Okay. Is the converse true? Like, are those the only solvers I ever need? The answer is actually no. I mean, there really are specialized algorithms that solve like f equals ma, really care about acceleration specifically, and we'll mention those at the end of our next lecture. So for instance, when we talk about structure preserving integration, well, we won't, but if we did, then that would matter quite a bit. Where like maybe you stagger the points in time when you have acceleration and velocity. If you guys haven't figured out yet, this is a topic I really love. So I'm happy to, you know, some of these other things, hardware is not so fun, but this stuff. Okay, right, so this is our reduction to first order, right? That we're going to have two variables in a first order system instead of one variable in a second order system. Okay, and so what that means is that we can have algorithms for just first order ODE. That's good. Okay, and so the typical way that we're going to keep making our notation even slicker here is we're going to make a new variable, big X, which just slams together all the variables, all the things that we don't know. And so now we can see that if we define our function f to be v and force like that, then Newton's law is going to be written in the form that we want. Okay. Of course, in a particle system, typically we don't just have one particle floating around. It would be pretty lonely. Particles, so rather we have a big collection of them that are moving and interacting, and that's no big deal either, right? So if I have n different particles, I'll make x be the whole collection of all the different particles, including their positions and velocities, right? And then our first order ODE, well, every other row is really boring, right? It's just like x1 prime is v1, x2 prime is v2, and then every other line is our physical force function. Okay? Right, so at the end of the day, another interesting vocabulary word, or way to visualize this, which I'll talk about while tying my shoe, is that if you look at the world of possible x values here, the term that we usually use is phase space. Okay? And remember that this is big X, so it could be, for example, in this diagram that the horizontal axis here is position and the vertical axis is velocity, right? Because in our language it doesn't really matter. And in that case, you can think of this function, little f here, as thinking of a vector at every point in phase space saying where stuff wants to go. Right? And so physical simulation's job in life really is just to trace out these different paths. Does that make sense? Incidentally, can anybody spot what this phase space is? This particular image? So let's trace through what these things look like, right? So here you're just going in circles, and up here you're kind of just flying off. This is actually a phase space for a pendulum, right? If you whack a pendulum hard enough, it just starts spinning around. And for smaller ones, maybe it just kind of goes back and forth. That's what's going on here. Okay, so of course there's a big issue here, which is, you know, as designers, we want to design all kinds of crazy functions that tell how different particles interact in our system, right? We don't want to be constrained by the ones for which we can solve this system of equations in closed form. Right? That'd be a pretty tough requirement. Also, we're lazy. You know, solving ODE is like one of these things you do in college and then never again. Mathematics is really good. So instead of that, what we're going to do is define algorithms that approximate the solution to this problem as a function of time for arbitrarily complicated functions f here, and they're going to work perfectly reliably and be a little bit less computationally expensive. So techniques for this are typically called numerical integration. Another word you see sometimes is quadrature, although I typically think of quadrature as like algorithms for computing the integral under a curve. These things are related. If you like these kinds of things, I encourage you to look at actually my textbook is a reasonable source. But in any event, today we'll talk about one very simple ODE integration strategy, and the next time we'll give you like 5 more, and we're going to see that they have different trade-offs in terms of quality versus efficiency. Okay. So today we're going to talk about the world's simplest ODE integrator, which is to say, well, if dx dt equals f of x, then in quotation marks here, I could kind of multiply both sides by dt. Obviously, this doesn't really make sense unless you're Leibniz, but that aside, it gives you some idea of what we're going to do. Right? We're going to say, well, our change in x is we're going to take f and multiply it by little dt in an increment, and that's our output. Yeah. And in fact, our algorithm has a name. This is called Euler's method, and it looks like this. We have some step size. That's our proxy for dt, right? And now if we add t naught, we want to go to t1. These are distance h apart. And what do? We evaluate little f at t naught, multiply it by h and add it to x, and that gives our nice one. Yeah. And so this extremely simple algorithm dates back to Euler. Euler's a pretty good old guy. Yeah. If you say Euler in this class, you're going to be in a lot of trouble. And it's sort of the most intuitive technique for integrating ODE. Yeah, and so there are a couple of vocabulary words and terms that you might hear thrown around, including coming from my mouth because I'm entrenched in this world. Sometimes people call this forward Euler. That's to contrast with something we'll cover in our next lecture called backward Euler. And another phrase we hear a lot is that your path is piecewise linear. And the idea is that you can kind of interpret this expression as between t naught and t1, you're approximating your motion with just a straight line. Right? And then at t1, you reevaluate your velocity, right? And you make a new line and you walk along that one. So it's piecewise linear. You go on a link in a straight line, and you change your direction, you go to another one. Okay. So let's draw a picture of what this looks like. So here's our ODE, dx dt equals f of x. Yeah. So here's maybe some x in phase space, right? So f of x is some vector saying where x wants to go. Yeah. So in forward Euler, I take that vector, I scale it by h, right? That's this green guy here. I add it to x, and there's my new precision. Did I solve the ODE? No, right? Like because notice that I went in a straight line, but the ODE is kind of waving around a little bit. Yeah. But at least for time, in small time steps, these are reasonable approximations of one another. Yeah. And in fact, that choice of h, that step size, controls the accuracy. Right? So the tinier little itty-bitty tiptoes you take in phase space, the better you'll capture the solution to your problem. And that makes sense, right? If you've ever seen a Taylor series in your life, you've probably seen a lot of arguments that look like this. So there's from an algorithmic perspective, like let's say I really only draw my frames once every 30 times a second. I could do 30 time steps. Right? I could say, well, between every frame of my animation, I do 1 time step. But I don't have to. Right? I could do 300. I could do 10 little Euler steps between every frame of my animation. And my approximation quality will get better, but I'll be better CPU time. Yeah, so that's the trade-off. Yes?
I was going to ask, in what circumstances do you see an f that depends on t?
In what circumstances do you see an f that depends on t? Sure. So let's see. What's a good one? So let's say I have a driving video game and there's traffic. And traffic is a function of time, and the way that I drive my car hopefully depends on the cars around me. That'd be a good one. I don't know. I would argue most dynamics depend on time. Or like, I can tell you, having watched a lot of you guys, that your behavior when the clock gets close to 4 p.m. is quite different from right now. So there's an external driver to the dynamics between you guys. Yeah. Okay. Great. So let's do a quick example. So here, let's forget physics for a second and say we wanted to solve this ODE on the plane. Anybody know what the solutions to this particular differential equation are? I see the right motion. Have you seen this YouTube video with this guy that's really good at drawing circles? No. Okay, so it's amazing. I wish I could give the guys my humor. So So here's the x-axis, here's y. And so the vector field, let's say I'm at x equals 1, y equals 0. So in that case, that would be this vector, right? Because at x equals 1, you're going to get 0, 1 as your vector. Similarly here, at y equals 1, this would be minus y, x. Right, so that's what this thing looks like. Okay, that's roughly what this vector field is. Right? That makes sense, right? Because of course the derivative of cosine is minus sine. That's kind of what you're seeing here. Okay. Right. So what happens if I use Euler's method? Let's think about it for a second. So in reality, the integral curves of this thing are circles. I'm not nearly as good as that guy on YouTube. But in Euler's method, what do? I don't. Oh man. Okay. In Euler's method, I walk along a straight line for a little while before I reevaluate my vector field. Yeah, and I reevaluate it here and so on. What happened?
You're going to get more of an octagon.
Yeah, it spirals outward. Yeah. So this is what Euler's method looks like applied to this particular vector field. Why is this a problem? Let's say I'm simulating a spring. Yeah? Actually a pretty common thing to do in a video game. You probably wouldn't render it as a spring, but lots of things get coupled together. Yeah? What's going to happen over time to my spring? Well, it's going to go crazy, right? Like for a little while, my spring might be kind of vibrating, and then it's going to get bigger and bigger and bigger and bigger, and so on. Right? So in other words, we call forward Euler an unstable ODE integrator. Right? And that means that over time, it can actually add energy to your physical system, which for a video game would be a pretty dangerous thing to have. Right? You can see that right here, right? That what should have been a circle actually kind of spirals out of control. Right. And actually that happens no matter how small h is. This isn't just like a fun math thing that I'm complaining about. This is actually a problem that we have to cope with. For example, here I'm sharing with you guys an image from one of my own research papers where we use these kinds of tools to take a 2D shape and deform it. So here I have this cute dinosaur, and maybe I want to move his head down. And the way that we were doing this was kind of computing vector fields that are little velocities of rigid motions. And the problem we had is if we took his head, dragged it up, down, and back, his head tripled in size. And that's exactly what's going on here, right? Because it's spiraling outward as we move. So essentially, what this calls for is that you need more accurate alternatives to your ODE integrator. And in our next class, we're going to talk about some other ones. Right? So our options right now are choose a tiny h, or just deal with instability. And incidentally, remember, this is physically based animation. So a totally reasonable thing to do here is detect that things are going out of control and just kind of quietly fix it, right? It's not physical, but it's kind of okay. Okay. As a fun, I'm trying, you guys haven't noticed throughout our lectures in this class, I'm going to try and give you interesting Google search terms for students that kind of want to dig around into cool YouTube videos. A fun one here is something called variational integration. So in our class, we're going to talk about two different types of simulators, one that looks like the left-hand side and one that looks like the right. Right, so here's explicit or forward Euler on the left-hand side. So that poor guy starts to spiral out of control. On the right-hand side, which is what we'll talk about for claw, we're going to add some dampening, which is going to essentially give you stability at the cost of the interest of your animation changing over time. One interesting question is, in the algorithmic regime, so not in theory, do there exist algorithms that preserve energy? Right? Like if I look over time, the kinetic energy doesn't change too much. And the answer is yes. These are called variational integrators. This is the beginning of a really cool thing. And actually some stuff that's not so hard to code. Okay, so right, so now that we at least have some algorithm for simulating physics, let's go back and talk about what physics we want to simulate. Yep. So in particular, we have to ask what is a force, and without getting too either philosophical or Star Wars-y on you guys, a force is something that changes your motion, right? And of course, what Newton tells us is that if there aren't any forces, you just move in a straight line. I always found that law to be a little bit redundant in Newton's laws, right? Like F equals ma covers that one. But in any event, right, your forces can depend on your location, the time, velocity. Can anybody give me an example of a force that depends on velocity? Yeah.
Damping?
Yeah, damping or wind resistance, right? If you fly fast enough, the wind, the faster you move, the harder the wind pushes back. Yeah? Not something that I experience here. Okay, so for point masses, forces are vectors. and the total force of some object, you just sum up all the guys that are active. Yep. Right, so for a couple of typical examples, you guys probably know this better than I have because the distance between you in physics class is much smaller. There are a lot of different things here. Obviously, the force due to gravity points straight down, and at least if you're close to the surface of the Earth, it's constant. One hack for smoke simulation is you just take that vector and flip it the other way. In other words, smoke tends to have the property that, because it kind of goes up and spreads out, it actually accelerates going vertically. So if you want reasonable smoke particles, you kind of randomize their position a little bit and flip their force. Of course, if you're simulating planets, then gravity does depend in distance, and it's inversely proportional. In other words, as you get closer, the force to gravity increases. And what that means is that your particles are independent. We know that, right? Because different planets circulate around each other. But let's think algorithmically for a second. So let's say I want to simulate 1,000,000 planets. Yeah? And I want to do one time step of Euler, which is certainly the simplest algorithm to the time step. Anything else is more computationally expensive. Yeah? Is this an easy thing to do algorithmically? No, right? Like how many computations am I going to do? 1,000,000 squared. Right? That's a big issue in physical simulation. Right? The scalability isn't just because we need to make that h smaller. It's also the fact that the more things you have interacting, like if you have n things interacting, then you have n squared interactions. Right? It's called the n-body problem. And that's actually kind of a problem algorithmically. So if you look at one of the big test cases for graphics processing unit for GPU is just simulating like a bunch of planets rolling around each other. And of course, the latest NVIDIA demos are pretty darn impressive. This isn't even the latest one anymore, by a long shot. So here's a whole giant planetary system, and you can see that this is being simulated on somebody's GPU in real time. Yeah. And probably if you guys wrote pretty naive code that just did like a double for loop or everything, it would look like that. Right. Algorithmically, is that the best we can do, by the way? That's not the lower bound. We talk a lot in program, in your intro algorithms class on like, you could do bubble sort is n squared. What is the other one? Like merge sort is n log n. I gave you an n squared algorithm. Is that as good as you can do? Yeah. So right. So the answer is actually no. You can do better. And there are a lot of hierarchical techniques out there. The basic idea here is that okay, Euler's method is approximate anyway. So there's a little bit of wiggle room in the forces I compute because at the end of the day, I'm going to get wrong. And as long as the incorrectness with which I evaluate my force is less than the incorrectness I induce by using Euler's method, then sort of that's okay. Right? There's a little bit of reasoning there. And so, for instance, there's an extremely famous, they had this really weird vote among my colleagues, which was like the 10 most important algorithms of the 20th century or something. And one of them that popped up that a lot of people didn't know is something called the fast multipole algorithm. And the basic idea here is that if you have a lot of planets that are far away, then roughly they act on you like one big planet that's far away. Okay? And so that leads to some kind of n log n style algorithm where, as my colleague has suggested here, what you do is take your points, and maybe they, here are my points in space. They're distributed in some fashion. And maybe I have a lot of planets just over here specifically. So I'm going to take space, and take a big point here into quadrants. Maybe I say, oh shoot, there's like a bunch of points down here. So I'm going to take that quadrant, divide it into quadrants, and so on. Right? And then what I can say is, like, if I am in this quadrant here, then I know anything in this quadrant is some distance away from me, right? And so if I think of this like some, in this case it's not a binary tree, it's a quad tree, yeah? Then sort of anything below this leaf can probably be just approximated with one particle. Okay? And that's the sort of clever tricks that people do in fast multipole to do this stuff fast. And in fact, it also inspired some fast rendering algorithms that we'll talk about later. The problem in my personal experience is that this stuff never works. That like the size of n you need before these things are very useful is like ridiculously huge. But anyway, that's okay. In terms of other forces that are interesting, one that we just mentioned is viscous damping, right? The idea that the faster I move, the harder resistance I get back. And of course things like wind resistance, fluid, and so on are like that. Right? These are also nice forces to have when you use Euler's method because they tend to remove energy from your system, which is a good thing if you're using an algorithm that tends to increase it. Yeah? So I think what you find in a lot of video games is a lot of wind resistance. Right. This is something called damping, and of course, if you have too much of it, it'll make all of your motion like move around in fluid. Right? Okay. And then one additional force that you should be aware of is sometimes people will just stick forces sitting in space without any physics behind them at all, but just to create interesting behavior. And it's remarkable what you can get, because remember the forces are second order effects, right? So even if I kind of flick off a particle in some constant crazy force field, you know, two particles that start at the same place but go off at different velocities will have very different behaviors. Right? So for instance, there's a really interesting kind of classic paper in the graphics world called curl noise, where the idea is that I'm going to simulate, I want interesting stuff to move around, but I don't want to have all these n-squared interactions, and I don't want to do something crazy like fast multiple. So instead, I'm just going to design a constant force field sitting behind my particles that makes kind of interesting behavior. And they can do remarkably interesting stuff. So all of these examples, if I recall, there's no dynamics here at all. It's just some constant force field sitting behind. But all of your particles have you know, slightly different initial positions, or maybe you do change your force field, but not in a way that makes the particles interact. There's just some god sitting behind the scenes that's messing with them, right? If you want to do this kind of stuff, typically your force fields tend to be kind of swirly, because that visually makes interesting motion. Okay? And you can see that like this almost looks like a, you know, physical simulation of like a, you know, what you might see in the Aeroastro department. The big difference here is that there's no physics at all. Yeah, and eventually these guys kind of swim away. Okay. Maybe interesting. These are fun to watch. Right, so if you look carefully, like this is definitely not physical behavior. Like a lot of these particles, there's like some weird eddies here that really don't make any sense. But essentially, you can design a reasonable force field just by noticing that you have a big triangular shape that's moving in a circle, right? And so the triangular shape maybe repels things a little bit from it and also creates some circulation. These are really easy techniques to implement and get really interesting behavior. Right. So of course, there are all kinds of different interactions. Another one that you might have seen is something called the Leonard-Jones potential. This is something that's like, I don't know, I have some relationships with friends like this. Like, you don't want to be too close. You know. So, like, you know, there's some distance that you kind of want to be in, right? Which is, you know, not too close, not too far, right? So if you get too close, you repel. If you're too far, you kind of want to get closer, but like not that strongly. And so this tends to actually create some reasonable simulations of things that are kind of nearly solid, right? So you have a bunch of particles that kind of want to interact in a grid, but you don't want it to totally collapse. And in fact, this is used sometimes for some of these simulations of you know, things breaking apart and fracturing. And so, right, or like, I think this is actually a more interesting version. So here they managed to use Leonard-Jones potential, right, which is saying that these particles do want to stay together if they can, to kind of simulate this thing tearing apart. And eventually a fracture goes through, they tear beyond that, you know, that point where the potential tears, and it just, you know, I think there's some gravity going this way on the red particles. So, any questions about the kind of forces you can design? And again, these are artistic tools. These are not physical objects, right? These are like different ways you can create interesting visual stuff by designing forces. This is not, you know, I don't know, maybe this is the way God works, but you know, this should not be mistaken for like something that captures the real world. Okay. Of course, there are a lot of different challenges in this pipeline. One of the big ones is collision. We'll cover a little bit of this in this course. If you want a deceptively hard course project that I've seen a lot of students fail at, it's taking a bunch of balls and throwing them into a square bin. And because, like, what are the collisions? Well, the collisions in that case are actually not so hard, right? They're just plane and a sphere, or a sphere and another sphere, so mathematically they're not so bad. But why does this get so challenging? It's because, you know, if I have a square bin, I have a sphere, I throw it in here, that's fine, and so on. And then eventually, there's a little bit of dampening, they start to stack on one another. Okay? And if you think about Euler's method, what's going to happen? Like, I'll do a little time step of the sphere here, it'll intersect a bit with this guy, and then I want to move it back. And then what happens when I move it back? Well, that affects all those other neighbors, which have kind of slid into place behind him, and so, right? And so, actually, resolving multiple collision between a lot of different objects is really tough. In fact, just last year, I think in 2D, somebody kind of worked out all of the details for like a 2D billiard table and all the things that can happen. And it's like one of these things is just no fun for anybody. Like if somebody asks you to code that, you should run. Yeah. Of course, there are a lot of fun eye candy you can do when you want to look at these particles. NVIDIA, by the way, the graphics card manufacturer, produces a lot of these things. Here's an example of sort of fluid dynamical-like thing happening behind a car. This CUDA, so it's no more than about, 10 years old. This is 0.5 million particles, and in this case, they have as an additional Eulerian grid sitting behind their fluid to capture the wind that's going on into the scene. And of course, you can get extremely dynamical and probably not terribly accurate fields of particles coming out of a sandy car. This, my neighbor's car looks like. And you can see it's interactive, like they're actually driving this car. You should take a simulation like this with a little bit of a grain of salt, right? The reality is that the GPU isn't just simulating that car; it also has to run Windows, and so I'm sure that they push this right to the limit of what your card could do. But probably if you were to write a video game, you'd want to be a little more conservative. So anyway, yeah. So this was 2009. So it was already a couple years ago. There are other interesting forces out there. Like I mentioned at the beginning of lecture, flocking birds in crowds is another great example. So there's an extremely famous technique here for simulating a crowd of birds that leads to a technique called Boyds. So each bird we're going to simulate as a particle. In this case, our particle is also going to have an orientation, like an angle glued onto it. And there's a little bit of modeling that takes place here. We're going to think of the bird as a little triangle, so he has a velocity pointing this way. And he has this little semicircle of vision here, right? And so the forces on this bird are going to depend on any birds he detects in this neighborhood here. Yeah? And what are they going to do? They're going to try and drag the velocity toward toward his neighbor. That's basically it. Okay? So you can imagine this isn't terribly difficult to formulate. Incidentally, bird apparently stands for birdoid. And while I don't consider this to be like the world's most earth-shattering or interesting thing, it is the beginning of a lot of different kind of crowd simulation techniques. So it's an algorithm, it's sort of based on somebody's phenomenological description of how birds interact, right? Like you tend to steer to avoid crowding, so maybe if you see too many people, you'll steer away. You have a line to the birds nearby, and cohesion, I guess, is to you want to be a member of the flock. And so here's an example of what this looks like. I think they used to live right near that address. Oh man, this is a terrible visual effects. You can see this is a very old technique. Oh, sorry. Anyway. Right, so actually I did link you guys to a demo of this. Actually, there are other versions of this, so maybe you come up with a predator one that the boys want to run away from. Still a little bit of a downer. A lot of these. Oh, this one is pretty sad. Wait, so the animation here is extremely simple. I think it's literally just this little animation sequence of like two triangles flipping up and down a little bit, and then the dynamics are governed by these rules that we mentioned. And by what's his name? Louis Armstrong. Okay. And I've included a link in the slides. You can play with this in your browser and like click and add little points to it and see what happens. Of course, this isn't just used in video games and to make like cute triangle birds. It really is actually used in production. And the main examples where you see this in movies are when you have crowds that there's just no way you could hire that many extras and have them behave and be in costume. So for example, a lot of this technology moved forward for Lord of the Rings, where you have these giant armies of like God knows what creatures marching upon each other. And it's really impressive to see what comes out. So here's one of the scenes that was modeled using some of this crowd simulation software. You'll notice that the camera never gets too close to the characters, because then you'd probably notice that something was wrong. And that the characters are like wearing all kinds of stuff over their face so that your uncanny valley doesn't get messed with. Right, and so in this case, obviously there's, I don't know, Gandalf or whoever in the front, and the rest of them are computer simulated, probably with a lot of guidance and hand tuning by animators. I'm sorry, this clip, unlike the last one, for some reason, has no audio. Yeah, so anyway, that's that. Right, so let's fill in just a few more details and then we'll be done for the day. So for one thing, as we mentioned, the particles come from emitters. That depends a little bit on your application, and typically you guys can just kind of figure it out as it goes. A pretty typical thing to do is to just kind of look at, like, you have some rate of particles per second, and you look at the time since the last particle that you made, right? And you sort of say that my probability of making a new particle increases with that time. It's a pretty typical model. Another thing you might want to do is, of course, again, artists want control, right? And these particles are kind of tricky to control. And so there's actually software out there. So I think this Max Payne thing was one of the early video games that made use of this pretty extensively. So what can happen is, for instance, maybe an artist controls the force field behind the particles and actually animates that. But the particles themselves move in an interesting dynamical system. So there's a piece of software you can download called Particle Effects, where you can actually control these kinds of things, including how the particles get rendered. And once again, of course, it's an application of splines. So in this case, maybe you control things like the rotation angle of your particle as a function of time, the distribution over colors that you're likely to see, I don't know, the distribution over masses of your particles, and so on. And that's actually what the artist controls. Yeah. So for example, maybe if I have a video game and I have some object, I crash my car into that object, a bunch of sparks fly, but then the sparks don't just like keep flying, right? Like eventually you run out of sparks, right? And so that would be the kind of thing that the artist might design, right? It's here, you see the bright orange sparks appear first and then stop flying pretty quickly. The red guys appear for a little longer and eventually they die as well. Yeah? And so this is what allows you to do some of these things that you see on the video clip. Yeah. Ah, come on, play.
Open it up. This is the particle system viewport. Over here is where you'll be making the particle system. This is where you'll be putting in values, and this is the curve. Time is how long it lasts for. Right now it lasts for 1 second.
So you see, these are kind of fun tools to play with.
Initial size is the size of the sprite particle which we're using. So right now it's 25. Hit control.
And eventually he's able to create a little
light
light
to brings up another one.
fire-looking material.
That one.
Probably by controlling both like the emission, the color, right? So here's probably a function of radius from the center. How many particles get emitted, where they tend to go, and so on. Okay? These are all artist controllable. Is this physics? No. Okay. Right. And so there are all kinds of different effects that people apply to these things, essentially to hide the fact that they're just points zooming around. So one of the common ones is to render with motion blur, right? Like again, maybe if I have a particle, remember the particle has a velocity, so instead of just rendering a point, maybe I'd render a little cylinder. And this is what's going to give me the illusion of having a bullet flying through, which of course is sadly a critical part of engineering nearly any video game right now. And so to make that even more complicated, oftentimes what people do is use things called billboards or sprites. These are like little GIF files on your computer. They're those like little post-it notes that fly by as the particle moves. And so rather than rendering a point, you render this little two-dimensional image. The reason why we call it a billboard is typically you always render that image facing the camera. so it just kind of rotates with you. But the scene happens far enough away that you don't really see that depth effect. Okay? In fact, you might still get some depth effect from the fact that you have a bunch of sprites or billboards for each of the particles, and as I move around this smoke, the position of the particles are changing based on my camera angle. It's just the orientation of the sprites that I'm putting is kind of artificial. Does that make sense? And so, in fact, there are all kinds of artistic tools for designing these things as well. So maybe here, I want this explosion, and I'm going to compose it out of these little basic units up here. And give a bunch of rules for, like, you know, if I'm close to the center of my explosion, I get this blobby thing, and farther out, it gets this small pieces. Yeah. Right. And so this technology and particle systems actually dates back to Star Trek II. I know a movie that I'm sure is close to many of your hearts, all the way back in the 80s. Which actually is one of the early computer graphics filmed for a lot of reasons. Another thing that these folks explored, which we'll cover later in this class, is constructing interesting landscapes by using fractals, right? And so, as many of you guys know, fractals make very interesting shapes in 3D, and you can use those to model the surface of the moon with some level of control. So I've included a link in the slide. You can see what it looks like in the 80s to make a particle system for movies. Right, but in any event, that's the basics of particle physics and simulation. Does anybody have any questions about how that goes? Or how it gets used in practice? It really does. This is like basically the fundamentals of how people do physics in practice. All right, so maybe we'll finish 10 minutes early then. Here's an animation of a head falling apart. And next time we'll talk about cloth and so on. So again, in the next couple of days, you guys' job is to finish your assignment. How many of us have started? Only like maybe a third of you. So, and yet, more than a third complained about that 1 week assignment. Right, but in any event, I'll see you guys on Tuesday. Don't forget your nano quiz. Come on.